Welcome to Mindcast, where we explore the cutting edge of technology and its profound implications for our future. I'm your host, Will, and today we're diving into what might be the most unexpected tech revolution of our time. You might think the next breakthrough in robotics will come from a traditional robotics lab, from some brilliant advance in mechanical engineering or control theory. But what if I told you that the key to creating truly intelligent, capable robots is actually being developed right now in the gaming industry?
Today, we're exploring how the relentless pursuit of hyper-realistic gaming experiences is accidentally building the infrastructure for the next revolution in embodied AI. It's a story that echoes one of the most important developments in modern artificial intelligence, and it's happening right under our noses. So buckle up, because we're about to uncover the unforeseen robot.
Let's start with a story you might already know, but probably haven't connected to robotics. In the late 1990s and early 2000s, the biggest challenge facing the internet wasn't artificial intelligence. It was much simpler. How do you organize the chaotic, exponentially growing mess that was the World Wide Web? Companies like Google weren't trying to build AGI. They were trying to solve web search, driven by the massive commercial opportunity in digital advertising.
This commercial drive led to something unprecedented: the creation of planetary-scale computing infrastructure, vast data centers, distributed file systems, parallel processing frameworks, and most importantly, the largest data set in human history, the indexed web itself. For years, this incredible infrastructure just sat there, a latent capability waiting for the right key to unlock its potential.
That key arrived in 2017 with the Transformer architecture. Its massively parallel design was a perfect match for the hardware the search era had built. The fusion unleashed an explosion in scale, leading to the predictable scaling laws and unpredictable emergent abilities of modern large language models. GPT, Claude, all the AI systems transforming our world today, they exist because of infrastructure built to solve a completely different problem. Now here's where it gets really interesting. I believe we're witnessing the exact same pattern unfolding right now, but this time, the commercial driver isn't web search, it's gaming. The multi-billion-dollar interactive entertainment industry is in the midst of a relentless pursuit of hyper-realistic virtual worlds. And in building the tools to create these digital playgrounds, they're inadvertently constructing the very infrastructure needed to solve robotics' most fundamental challenges. Let me break down exactly how this is happening. The gaming industry is being driven by three core demands. First, there's the quest for physical believability. When you're playing a modern game, you expect objects to behave realistically. They should collide, deform, and interact naturally. But traditional physics engines are computationally expensive, so the industry is turning to AI to create high-fidelity approximations that are efficient enough for real-time gameplay. The industry uses a fascinating technique called baking physics into neural networks. Developers use high-fidelity physics engines to generate massive data sets of specific physical interactions, then train neural networks to learn compressed, lightning-fast mathematical models of that behavior. What you get is specialized AI that can simulate realistic movement in microseconds, exactly the kind of high-performance physics simulation robots need. What you end up with is something remarkable. A CAPE AI engine that can simulate realistic fabric movement in microseconds, orders of magnitude faster than traditional methods. Sure, it can't simulate a rolling ball or a bowl of Jell-O, but for its specific purpose, it provides a visually plausible approximation that's exceptionally fast. This is exactly the kind of specialized high-performance physics simulation that robots need to understand how objects behave in the real world. The second major driver is procedural content generation, or PCG. Think about the scale of modern open-world games.
Creating every mountain, forest, building, and quest in a virtual world spanning hundreds of square kilometers manually would be prohibitively expensive and time-consuming. So the industry has turned to algorithms that can automatically generate game content and assets.
But here's what's exciting. AI is making procedural content generation incredibly sophisticated. Instead of random variations, AI-driven systems can learn the underlying rules and aesthetics of game design. Machine learning models trained on existing levels understand what makes them enjoyable and coherent, then use this knowledge to generate new content that maintains design consistency while offering novelty. Modern techniques employ generative adversarial networks to create realistic textures and 3D models, reinforcement learning to design levels that meet specific gameplay criteria, and algorithms like wave function collapse for coherent world generation. This represents a shift from randomness to intelligence in content creation. This technology for creating vast, varied virtual environments is exactly what robotics needs to train AI systems on diverse scenarios. The third driver might be the most revolutionary: generative NPCs, or non-player characters. For decades, NPCs have been a source of frustration for players. They operate on rigid, pre-scripted logic, exhibiting repetitive dialogue and predictable behavior that breaks the illusion of a living world. Player surveys reflect this dissatisfaction. 99% of gamers believe more intelligent NPCs would positively impact gameplay, and 76% explicitly want characters with greater emotional and situational awareness. Enter generative agents, powered by LLM technology. Instead of dialogue trees, these NPCs are given biographies, motivations, and memory streams. They use language models to generate dialogue and actions based on their personality, memories, and current game state. Stanford research showed these agents exhibited emergent social behaviors, planning parties, forming relationships, all without explicit programming.
NVIDIA is productizing this with their Avatar Cloud engine, which combines speech recognition, language model dialogue generation, and real-time facial animation. The result? NPCs that can engage in spoken, open-ended conversations that react dynamically to what players say. But here's the kicker. This technology for creating autonomous, intelligent agents that can navigate complex social and physical environments, that's exactly what we need for robots operating in the real world.
Now, let's talk about how all of this is being unified into a coherent platform. NVIDIA, with their dominant position in graphics processing and deep AI investments, is architecting a comprehensive ecosystem designed to serve both the gaming market and the robotics market. This isn't accidental convergence. It's a deliberate corporate strategy to build a foundational platform for simulating reality. At the core is Omniverse, a development platform for building, connecting, and simulating 3D worlds and applications in real time. It's built on Universal Scene Description, or OpenUSD, an open-source framework originally developed by Pixar. OpenUSD acts as a universal language, like HTML for the 3D internet, allowing different tools like Maya, Blender, Unreal Engine, and Unity to interoperate seamlessly. This breaks down the data silos that have historically fragmented 3D content creation.
Built on top of Omniverse is Isaac Sim, NVIDIA's specialized robotic simulation application. Isaac Sim leverages the platform's RTX real-time ray tracing for photorealistic rendering and PhysX physics engine for accurate dynamic simulation. It's explicitly designed to solve the sim-to-real gap, the persistent problem where AI models trained in simulation fail when deployed on physical robots.
Isaac Sim addresses this through multiple approaches. Physically accurate simulation using mature gaming physics engines, realistic sensor simulation using RTX rendering to accurately model camera, LiDAR, and radar data, and synthetic data generation through domain randomization. systematically varying parameters like lighting, textures, and object positions to create diverse training datasets that force AI models to learn robust, generalizable behaviors.
Layered on top is Cosmos, NVIDIA's platform of generative world foundation models. Instead of manually constructing every training scenario, Cosmos can take a 3D scene and transform it to entirely new conditions, different weather, time of day, environmental textures. This multiplies training data diversity by orders of magnitude. Neural rendering technologies can reconstruct interactive, photorealistic 3D scenes directly from real-world sensor data.
To understand why this gaming-driven infrastructure is so crucial, we need to examine the fundamental challenges that have held robotics back for decades. Despite remarkable progress, autonomous robots remain largely confined to highly controlled settings like factory floors and warehouses. The transition to the chaotic, dynamic nature of the real world, our homes, offices, cities, has proven to be an immense hurdle.
There are three core challenges. First, the sim-to-real gap. Even highly advanced simulators are approximations of real-world physics. Minute discrepancies in friction, joint elasticity, or contact dynamics can accumulate over time, causing robots to behave very differently than expected. These include dynamics mismatches, perception gaps where clean simulated data differs from noisy real-world sensors, and embodiment mismatches where small physical differences lead to unexpected behaviors.
The second challenge is the unstructured world problem. Factory robots are efficient because their environments are engineered for predictability. But human environments are dynamic, cluttered, and unpredictable. A domestic robot must identify novel objects, navigate changing clutter, and interact safely with unpredictable humans. Pre-programming solutions for every contingency runs into the same combinatorial explosion that stymied early symbolic AI.
The third challenge is the data bottleneck, and this is the big one. To overcome the limitations of hand engineering and tackle unstructured world complexity, robotics is following the same path as natural language processing and computer vision, moving toward large-scale foundation models. These are AI systems pre-trained on massive, diverse datasets that can be quickly fine-tuned for new tasks, demonstrating the generalization that's been so elusive in robotics.
But here's the problem. Robotics has no equivalent to the vast text and image datasets that train language models. The necessary data for embodied agents isn't static text or images, but rich, multimodal streams of interaction data. Synchronized video, proprioceptive feedback, tactile information, all linked to motor commands. Collecting this in the physical world is extraordinarily difficult and expensive. This data bottleneck is the greatest impediment to building powerful robotics foundation models.
And this is where the gaming infrastructure becomes absolutely crucial. The only viable path to generating the petabytes of diverse, high-quality interaction data needed for robotics foundation models is through high-fidelity simulation. Essentially, building a data factory for robot training. The gaming industry, in its pursuit of entertainment, is building exactly this factory.
Game engines like Unreal and Unity, coupled with RTX ray tracing, provide the photorealism necessary to train robust perception models. Gaming physics engines converged with precision robotics simulators create the foundation for physically plausible interaction data. Procedural content generation tools enable domain randomization at unprecedented scale, creating near-infinite training scenario variety.
This points to a revolutionary strategy for solving the sim-to-real problem. Instead of creating one perfect simulation, which may be impossible, the solution is creating a data generation pipeline so vast and varied that the resulting AI becomes immune to minor inconsistencies. If you train a robot on millions of simulated environments with slightly different physics, lighting, and object properties, it learns a generalized understanding of physical interaction.
What we're witnessing is a powerful symbiotic flywheel between gaming and robotics. Gaming funds foundational research in computing, rendering, and physics simulation through the massive video game market. Robotics inherits this technology without bearing the full development costs. The unique demands of robotics push development of new AI architectures within these simulation environments, and breakthroughs in physical AI feed back into gaming, inspiring new genres of interactive entertainment.
Imagine open-world games populated not by scripted NPCs, but by truly autonomous AI agents with persistent memory and emergent goals. Or physics-based puzzle games that leverage a deep, learned understanding of material properties and dynamics. The gaming industry provides the scale and economic engine, while robotics provides the grounding in physical reality that pushes AI capabilities forward.
Now, there are valid concerns and challenges that remain. Game physics engines prioritize performance and visual plausibility over scientific accuracy, though this gap is narrowing. The computational cost of training massive foundation models on petabytes of synthetic data requires enormous resources. And even with unprecedented simulation fidelity, there will likely always be a last-mile problem requiring final validation on physical.
But these challenges don't diminish the fundamental insight. The core challenge of modern robotics is being reframed from a mechanical engineering problem to a data problem. The critical path to more capable physical robots lies not in building better hardware, but in building better virtual worlds to train them in. The gaming industry, pursuing entertainment, is unintentionally building the very data factory that robotics needs.
Looking forward, I believe we're approaching a potential breakthrough moment. Just as language models showed emergent abilities when scaled beyond certain thresholds, robotics foundation models trained on gaming infrastructure might cross similar critical points. We could see the emergence of generalized physical skills, dexterous manipulation, adaptive locomotion, intuitive tool use that are simply impossible with today's data-constrained methods.
The story that began with a desire for more believable explosions in first-person shooters, realistic character animations in RPGs, and smarter NPCs in open worlds is converging on a singular technological capability: the ability to create, simulate, and scale digital twins of reality with unprecedented fidelity. This is precisely what's needed to overcome the data bottleneck that has constrained robotics progress for decades. The parallels to the modern AI revolution are striking and, I believe, predictive. The commercial necessity of organizing the web created the infrastructure that enabled large language models. Now, the commercial necessity of creating immersive, interactive entertainment is building the simulation and synthetic data infrastructure for the next generation of embodied AI. The Unforeseen engine that gave us sparks of general intelligence is being followed by a new unforeseen engine that may give us the unforeseen robot.
The new frontier of AI is physical intelligence. The path to achieving it isn't through handcrafting rules, but through learning from vast amounts of experience. The gaming industry, in its quest for entertainment, is building the very factory that will generate that experience at planetary scale. We're witnessing the birth of a new technological paradigm, where the distinction between virtual and physical worlds becomes increasingly meaningless, and where the pursuit of digital dreams enables the realization of robotic reality.
That's all for today's episode of Mindcast. If this exploration of gaming's unexpected role in robotics has sparked your curiosity, I encourage you to keep watching this space. The convergence is accelerating, and the implications are profound. Until next time, keep questioning, keep exploring, and remember, the future often arrives from directions we least expect. I'm Will. Thanks for listening.